has two one. It has X. Oh, is this a too thick? Probably this one. X and theta. Okay, right. So you have two coordinates. You can see there are two coordinates to describe the motion, but you can see that these two coordinates actually is dependent of each other. So this is a rainbow. Let me find a better color. Okay. Right. So here, right. So this you don't for when you because later maybe ask you to model some system. So when you see the description system, so you just not see what is the degree of freedom depending on the quality that you can see, or you can find out. You need to study whether is it independent or dependent. For example, this two actually is dependent. So the x can be expressed by theta. Right, so here, what is relationship between x and theta? Anyone can tell me? Can you see if I don't enlarge the screen? Right, is that big enough for you? Okay, for some questions here, so I will upload the material here, but I didn't upload now before your class. The reason is I don't know whether how many of you can print. Okay, and if you look at from the screen, then you cannot look at this screen. So, but it's up to you. If you want, I upload before the class. I can upload before the class, or I will upload after the class. Any other questions? Because when I'm looking at the point, I cannot see the message here. Okay, so what's the relationship between these two coordinates? I'll try if I screen whether I can still write, okay? But I cannot erase. So just see, I just keep this, probably enlarge a little bit, okay? Right, what's the relationship between these two coordinates? Right, so if we see this is L, right, the length of this slider is L, right? So actually Lx, I see x equal to L, how much cosine theta, right? Right? Is there x equal to L cosine theta? Right, so you can see that x and theta, right? So actually they are dependent of each other, right? So this is still a single degree of freedom, okay? Right, for the B here, so this is very simple. You just see there the x, okay? Right, only one coordinate. So this one as well for this torsional system, right? Also has one to describe the system and theta, right? So here is you need to, right? So you need to be careful. It asks you to model some system, right? So you need to judge. So because different degree of freedom, right? So you of course this all these formulas are different. Okay. Right, any questions here? x equal to, yeah, right, sine theta first. X should equal to sine theta, right, to okay, sine, right, sine, right, so this is here, right, this is sine, not cosine, right, if you give a y here, then becomes cosine, right, right, so this is a tricky part. So when you judge the degree of freedom, so must see whether it's dependent or independent. Okay? Right. Example of second degree of freedom. So this for here in our current our assignment. So this actually is for multi-degree system. So it's very clear. So like something like this, mass and spring. But because the probably or not probably, very likely we will change the type of assessment. So probably give you a more complex system for you to model. Okay. So this is so that's why I want you to know more about how you can model the different system. Okay. Right, so for not just the spring and mass, but of course for this kind of spring and mass, you can easily see this has x1, x2, right? So it's second degree of freedom. And for this two rotor system, right? So you have theta 1 and theta 2. Okay. Right, so let's take a look at this system. So you can take a look at the C, the C, right? So what is the coordinate here? Right, so actually one is to describe the mass here, right? So you can use the X, right? The X is for the mass, right? Another is small x, right? Small x or the theta, okay? So here the x and the theta here, so they are dependent, okay? So these two are dependent, right? So this is dependent each other, so you can, and also the y, okay? Right, so this x, y, theta here, actually they are all dependent. So the independent coordinate, right, is x, a big X and theta, okay? Or big X and small x, or big X and y, okay? Right, so here actually you can see when you come out the governing equations, you can also have different set of coordinates. So there's not only one way to solve the problem, you can see. Right, so here x, similar x is equal to sine theta, L sine theta. So the xy has a relationship is x squared plus y squared equal to L squared. Okay, so x and L is equal to this sine, right? Okay, so this x, y, theta, they are not independent. Okay, so dependent. Right, so only big X and small x. So you have three possible set of coordinates here. Right, if you have question, you can free to type. I will, after a few minutes, I will come back to take a look at the laboratory. Okay. Okay. So here is an example of 3 degrees of freedom. So basically for our calculation, we may just stop at 2 degrees of freedom. Some example is 3 degrees of freedom, but very few, I guess. So here, most 6 calculation may stop at 2 degrees of freedom. Okay. Right, so here's 3 degrees of freedom. Right, so this for the mass spring, it's very simple here, x1, x2, x3. So this, right, so theta 1, theta 2, theta 3, for this shaft with the, right, for this pendulum system, right, so it's many, many coordinates here, theta 1, theta 2, theta 3, x1, x2, x3, y1, y2, y3. But you know that theta 1, x1, y1, actually they are correlated to each other. So basically, you can just using one theta 1, theta 2, theta 3, or x1, x2, x3, or y1, y2, y3, right, to represent the coordinate for this system. Okay, right. So this is a 3 degree of freedom. So any questions for the degree of freedom? So this actually is very important later if you want to model the system. Okay, right. First is you need to describe the system, but there's not the only way. Right, so you actually have alternate ways. Right, so for this infinite number of degree of freedom, so this is for some continuous structure, for example, a cantilever beam here. Right, if it's for continuous distributed system, so you have infinite number of degree of freedom. Of course, it's very hard to solve based on this kind of degree of freedom. So basically, even in the computer models, so we will have finite number of degree freedom, but we have just many number of degree. Okay. Right, finite number of degree of freedom, which is called discrete or lumped parameter systems. Okay. Right, of course, more accurate results obtained by increasing number of freedom, okay, degree of freedom. But of course, you know that the complexity also increase when you increase the number of degree of freedom. So that's why so we can ask the help of the computers if you want to model them as a large degree of freedom or even right finite number of degree of freedom system. Okay. Right, any question regarding the degree of freedom? Okay, so then we come to the classification of the vibration. So you might already know that we just review the topic. Okay. So later when you solving the problem, the first thing you need to do is to classify what kind of vibration it is. So you can just refer to different formulas. Okay. Right, for free vibration, okay, a system is left to vibrate okay, on its own after an initial disturbance and no external force acts on the system. Right, so for example, the simple pendulum, right? Right, if you or you have a simple mass spring, okay, free vibration, right? Forced vibration. So forced vibration is a system which is subject to a repeating external force. Okay, right. So for many machines, motors, so you have this repeating external force. Okay, oscillation arises from the engines, diesel engines. So this for the forced vibration. So it's important is we need to be aware of is the resonance. Okay, right. When the resonance will occur, when the frequency of the external excitation of the forces will be the same or very close to one of the natural frequency of the system. Okay? So that's why we later we need to find out the natural frequency of the system. Okay? Right, so we need to, for the engineering design, we need to have the solution, okay, to avoid the resonance, okay. Right, so as we mentioned, the resonance will cause devastating effect of the system, for example, the failure of the system. Okay. Right, undamped vibration, when no energy is lost, okay, or dissipated in friction or other resistance during oscillation, we call it undamped vibration. For many systems, actually the energy loss is very small, so we can neglect it. Okay, also we can also approximate it as undamped vibration. Right, for damped vibration, so when any energy is lost or dissipated in friction, many times is dissipated, right? So as heat, okay. Right, so if you have other resistance during the oscillation, so you call damped vibration. So you have different types. Some is itself has a damping effect. Some is you have special design dampers, right? To try to dampen the vibration. Okay? Right, so it's called damped vibration. Okay. Right, so this is another type of classification of the vibration. Okay. Right, so we call linear vibration or non-linear vibration. Right, so this probably you didn't learn before. So for the any if all the basic component of vibratory system, for example, the spring, the mass, the damper behave linearly, we call it linear vibration. So remember the spring, it has F equal to Kx. So this is a linear. Okay, so the damper as well is Cx dot. Right. Right, so we call it linear behavior. Okay. Right, so F. Okay. Right, nonlinear vibration. If any of the component behave nonlinearly, we call it nonlinear vibration. So basically, in this class, so we basically deal with linear vibration. So you can see the formula we given later. The y is always common. So is basically is linearly, okay, linear vibration. So nonlinear vibration is much more complex than linear vibration. So basically, we need to also ask the help from the computers. Right, for deterministic vibration, so if you already know the force, for example, you know the force, F is equal to, let's see, I'll give you a, If you already know the force, for example, you know the force function respect with t, right? So this is, you already have the function, you know that. So this is deterministic vibration. Okay. So the excitation, right, the force of motion is known at any given time. Okay. So this is known. Okay. Right. So this is basically for many machines. Right. So you have known vibration. But if not know the vibration, not know the value of magnitude of excitation, right? Ft, right? So it's called random vibration, right? So for example, as mentioned, the wind, okay, right? So it's very random. Okay? Right. Also, for some washing machine, when it's operate, so it depends on how the thing that you washed in the washing machine, right? So how they locate them, so you don't know the mass, right? So the distribution of the mass, they might change. So you can also see is random. Okay, right. So here is the what it looks for the deterministic excitation. Okay, so the vibration is excitation force, right? So it's has known behavior, but if it's random, right, so this is random. Okay. Right, so after we introduce the classifications, also the number of degree of freedom, so we take a look at how we do the analysis. So this is a general vibration analysis procedure. Right, so we have 4 steps. Right, so first step is mathematical modeling. Right, so this is our first step. So basically for mathematical modeling, later we'll show some example. So you can see that you can either modeling in a simple way or in a more complex way. So how you're going to model it, of course, is affect the accuracy of your analysis. Okay, but if you make it too much complex, they will make it very difficult to get to analyze, right? So you need to balance this. Okay. One thing you can do is you can model this way, but you can check your results, check the analysis whether it's appropriate, whether it's very close to the real performance, okay, real vibration, right? But if it's not, then you can modify your modeling, okay? Find the one that is more close to the real vibration, okay? Right, second step is derivation of governing equations. So for the governing equation, basically is from the principle of dynamics, okay? So from the principle of dynamics, okay? Okay. Right, so basically we have two type of, right, so one is we use the Newton's second law, right? So another is using the energy conservation. So I am not very good when writing on the screen, but you know it, it's fine, right? Right, so one actually is to analyze the force. One, right, is analyze the energy. Okay. Right, so from here, actually we can get equation of motion. Okay. So after you get equation motion, so you also have some initial initial conditions. For example, the initial displacement, initial, if you know, initial velocity or initial acceleration. Then from this boundary conditions, so you can come back and they find, right, find some constant, okay, in the governing equations. Okay. Right, so solution of the governing equation. So this is depending on what is the equation you derived. So probably is first order differential equation, maybe second order, or even more. So depending on what equations you get, so you can mathematically solve using the equation of motion and the boundary conditions. Okay. So then you can interpret your result. Basically, what they're interested to know is the natural frequency, right? Omega n. Okay. So from here you can find also the period, the frequency, right? So these are actually related to each other, right? And also the response of a system, right? So the displacement or maybe theta, right? So the velocity and acceleration or theta dot. Okay. So it depending on what is the system is. Okay. Right. What is the coordinate you are using? Right. So you can interpret the results. Okay. Right. So here we take a look at some examples for the modeling. Okay. Right. Right. So this is example modeling of forging hammer. So right. So this is actually the block, right? To which the hammer will forge on that. So you have an elastic pad. You have a foundation block. So this is like the floor or ground, the soil. Okay. Right. So we'll take a look at this. How you can do your first step. The first step is mathematical modeling. Okay. Right. So remember here, you need to remember that you have the basic element in the vibratory system. Right. You have the mass, spring, damper. Right. So this is your basic elements in a vibratory system. Okay. So how you can model them into this basic element. So as I mentioned, there's not only one way. So you can either model it in a simple way or more complex way. But it depends on the results you get, whether it's it's very accurate enough or not. If it's not accurate enough, then probably you need to further modeling. So here you can see the first approximation. Here is you put this anvil and the foundation block together, right? So this together, Right, so this together as mass, right? Also itself, it has inherent damping effect and stiffness. So you have the okay, so sorry, so okay, so this one is not so only here it didn't consider the damping and stiffness here. Only consider as a mass. So here is anvil foundation block here. Right, so the damping and the stiffness is from the soil. Okay, so this is from the soil. Okay, okay. Right. So the soil is modeled as a damper and the spring. Okay, so here is only the mass. Right, so this is the first approximation. Right, so second, maybe later you find it's not that uh, accurate enough. So it has a further approximation here, right? So it separate, okay? Separate the anvil, right? So separate the anvil and the elastic pad and the foundation block, okay? Right, so the foundation block here, it didn't consider, so because it need to, if you give you a problem, so you need to read carefully what you may consider or from your experience or from the information you can get. So here the foundation block, it didn't consider the no damping, no stiffness, just as a mass. So here only as a mass. Okay, so the soil go to the damping and stiffness. So as you can see here, elastic band, right? So elastic band means elasticity, right? Right. So because it has elasticity, so you have this damping. It has its own inherent damping and stiffness of elastic band pad. Okay. Also here is elastic pad, right? Right. Right. Okay. Also here the anvil itself is a rigid block as a mass. So you can see here. Uh, uh, right. So this foundation of block. These are two mass, and the anvil is here itself is two mass. So here the stiffness and damping is come from the electric pad and the soil. Okay. So any questions here? Right. We take a look at another example to give you some sense of modeling first. So here is similar to what you might have. So you need to read so carefully. So here it says the figure shows a motorcycle with a rider develop a sequence of three mathematical models of the system for investigating vibration in the vertical direction. Right, so here you can see here vertical in vibration vertical direction. So you just consider the vibration here, okay, in the y direction. Right, so here consider elasticity of the tears. So when you read, you can see the tear has elasticity, right? The stress has elastic damping elasticity and the mass of the wheels. For the rider, it has elasticity, damping, and the mass. Okay, okay. So when you read, okay, right, how you model this? Right, so actually it gives you the three or four, B, C, D, E, four different type, four different modeling. Okay. Right, here has some a description. Okay. So for this model here, B, right? Right. So in this model, equivalent stiffness K equivalent includes stiffness of pairs, stress and rider on the equivalent damping constant, including the damping of the stress and the rider. Right. So equivalent mass include the mass of wheel, vehicle body, and the rider. Okay. So it just make one mass system. So tells you what is the K equivalent, C equivalent, M equivalent. Okay. Right, you can see this is a simple model, but it might be too simple. So here it develop a more accurate or more complex model in the figure C. So here in this model, you have two mass. Okay, so we have a vehicle body MV and the mass of the rider MR. Okay, shown as a single mass, MV plus MR. Okay, so here is still a single mass. So here still still one mass, MV and MR. Okay. Okay, so now three mass system. So MV plus MR, and also the two wheels. Okay. Right. So the elasticity, because cannot see, maybe I put my notes on the side so I can. You look at the figure same time. You look at the description here. Okay. Right. So here, when the elasticity and the damping of the rider are considered, the refined model. Okay, this is a description of D. Okay, so here maybe you just take a look at the figure here. So you have so in this model you have MV plus MR, which is here vehicle and the rider. Okay, right. So here struts, the strut. Okay, so the strut here, two strut. Right. So we have stiffness and damping, because actually it tells you here for the strut has elasticity and damping. Okay. Then the tire, two tires. Tires has the only elasticity. So here is only elastic for tires. KTT for tires. So you can take a look at this subscripts here. Okay. Right. So why this? Because actually it's already described here. Which one has elasticity? Which one has elasticity and damping? Which one has a mass? Okay. But if we didn't tell you, then you need to judge using by yourself or by the common sense. Okay. So or by not the common, probably just the from the information of the system, you know how much mass is this one, how much elasticity that one, how much damping. If you have the information, or you want to try to find out the information, so you can help you to construct the model. Right. So the difference from D and C is so it separates the MV and R. So for the mass of rider, so rider itself is said it has elasticity and damping. So you have this subsystem here. So then you have the vehicle. Right, so vehicle is on the struts. The struts also has elasticity and damping. So right, so this is connected to the wheel. Okay, so wheel right is on top of the tires. Tire only has elasticity. Okay, so this is right, a refined model based on C. Okay. Right, so you can see that you can have different models. But which model you are going to use? Of course, this is more accurate. So this is one is more accurate, but they might think it's more complex. So depending on how accurate result you are looking for, so you can select the right model or appropriate model. Okay. Right, so this is another developed model. It actually is trying to simplify the problem. Right, so this is a combine the two tires, two wheels together, two struts together. Okay, and MB and MR. Okay, right. So we didn't consider the right. So this is a simplified model based on this one. C. Okay. Okay. Right, later I will upload the slides so you can take a look at the description. But actually, this from also from the textbook. So the textbook is actually has ebook available. I don't know whether you realize or not. So actually, I remember I have the link. Okay. So on the textbook as well. So you might need to access the textbook. Anyone know how to find the textbook? At least available in Canvas. We have a reading list, or you have the right on the reading list. You have this book. Okay. So there's the ebook as well. Also, another one you can reach this book if you want to read more. So you can take a look at the textbook. Okay. If you let's let me try. From the modules, course resources, you can also find the book. Okay, so it's a let me see the link is okay. So probably I share give you take a look. If anyone want to read the books, so they can read the books as well. So here is available. Right, so you can see when you go to our Canvas course site, right? You can click on the modules. If you can click on the course resources, right? So there is a link to the textbook. Okay. Right. So for those who want to read more, because we might have essay questions later, so you might need to the textbook. Or you can use other textbook as well. So if you want to look at the textbook, you can go here and then click here. So you can read online, okay? Or you can download the PDF. Okay. Right, so this is our textbook. Okay. Right. So I thought you might use this because we might have essay questions later in the assessment. Okay. So here is the different chapters. Of course, this is much more than what we are going to learn in this class. So this class actually is the start of the mechanical vibration. Okay. So there are many more you can see. Okay. Topics. Okay. So anyway, you can go if you want to take a look at the textbook. Also, another way you can go to the textbook is a reading. Let me see. Okay, so here it didn't show. So anyway, so you can try by yourself if you want to try now. Right, so I think you might use this. Very likely. Okay. Right, so here there's another one. Another is from the reading list. Reading list. I don't know whether you can directly read here or not. But anyway, you can search on the. Okay, so you can also view online here. Okay. So two links. Okay. Right. Right. In case later you need to find more, and not only simple calculations. So you might need to refer some reference. So you can recommend the textbook is your first reference. Okay. So any questions so far? So we will back to our PowerPoint. Okay. So here actually we will just show you is some example for mathematical modeling. Right. So here you see that in the mathematical modeling, also very important element here is spring. So here we have a special introduction to the spring element. Spring element. Right. So as we mentioned before, we said if the every element it behave linearly, it's a linear vibration, right? So here is a spring, is a linear spring or not? So of course in this class we basically use a linear spring. So linear spring is a type. You all know what spring is, so I don't need to show you. So linear spring is a type of mechanical link that is generally assumed to have a negligible mass and damping. Right, so the spring force is F equal to Kx. So this is a linear equation. Okay, F is spring force, K is spring stiffness or spring constant. Okay, X deformation. Respect to its original length. Okay, right. Displacement of one end with respect to the other. Right. So for spring, if you consider its potential energy or work done by the spring, okay, so the energy, the potential energy of the spring is, so V is expressed for potential energy, right, called half K delta square. Delta is the change of length of the spring, okay? Half K delta square, okay? So right, so as you might have a very clear understanding of the spring, but here is I just want to draw your attention. When we are seeing spring element, of course not just spring. It might be anything that has elasticity. So here you just say give you some simple structures to show you how they can be simplified as a spring. Okay, as a spring. For example, so this rod, right? So this rod can be equivalent spring. So we can find out its spring constant. Okay. Right. So we know that this rod, if it had elasticity, so when you apply the force F at the end, so you might change the length to delta. So you know F spring constant K equal to F over X or over delta. Okay. So we receive over delta. Okay. So you can find its spring constant. So how much is delta? Right. So this is what we want to know here, right? So how much is delta? Right, so remember delta is equal to how much? Epsilon L, right? Epsilon L, right? So string times L, so string equal to sigma over E, right? Right, L, right? Sigma equal to F over A, E, L, okay? Right, so here you get K equal to F over delta, so you can have F over delta is equal to how much? Is AE over L, right? So you can have the spring constant, equivalent spring constant, equivalent linearized, because we, to be simple, we just see this linear spring. So K equal to AE over L, right? So this is spring constant for this simple uniform rod of length L, which has a cross-sectional area A and Young's modulus E. Okay, so this is a spring constant for this rod. So you just change your like a rigid image of the spring. So spring can be anything with elasticity. Okay. Right, so here take a look at another example is a cantilever beam. Right, so for the cantilever beam with a mass at the end, so how much is the K? So we want to find out K. Right, so the equivalent spring become from this cantilever beam is like a mass spring system like this one. So here K equals 3EI over L plus 3. Anyone know how to find out the K? Right, so this actually is derived from the deflection of the beam. So you learned solid mechanics before, right? So maybe we just say just right. So if we go back, take a look the beam deflection formula. Right, so show you some. So we just search online beam deflection formula here. So we just click on any image. So probably this one. It's not big enough. So here, so the cantilever beam is similar like this one, right? Right, so the delta equal to P over L33EI, because this is force is applied at the end. So this P actually is come from the mass, okay? From the mass, okay? So anyway, so you can see here you have this one delta max equal PL to 3 over 3EI, right? Right, so the case, the spring constant K is come from P over delta max is 3EI over L to the 3, okay? Can you see? Because I show here is very small. Probably you might not see very. Anyway, it's here on the cantilever beam. Probably if you have on the, I think you are on the computer or you use your phone, so you might see. Okay. From this here. Okay. Later I will send the PDF to you during the break. Okay. Okay, I just saw your message. So I know that if there's new message, they show in the red. Okay. Right. So if you're on the computer, you can search by yourself beam deflection formula from the cantilever. So you can from here the delta max. You can get P over delta is the same. Okay. Okay. All right, so this is how the spring constant come from. Right, so okay, so here actually has so static deflection of beam at the free end is given by you can get this from the beam deflection table, or you can derive by yourself. So W is the weight of the mass m, E young modulus, I moment inertia of cross section of beam. So you will get K equals 3 EI over L to 3. Okay. Right, as you see that, so for the modeling, you might have different, you might have more than one springs. So here is, if you have more than one springs in your model, so here we see some is in parallel, some in serial. So what is a K? K equivalent. So for example, this you have two springs, you have a plate. Okay. Right, so here you have two spring in serial, you have mass. Okay, so this is in parallel, this is in serial. Right, so I will not go to how you derive this K equivalent. So, and you know that for springs in parallel, right, if you have n spring constant in parallel, then the equivalent spring constant K EQ is K equal to K1 plus K2 plus Kn. Okay, if string is series, so if we have n spring constants K1, K2, Kn in series, then equivalent spring constant K eq is right 1 over K eq equal to 1 over K1 plus 1 over K2, right? So you can remember this. If we have more than one springs, so any questions so far? Probably we will just go on. So we will left the examples in the next session. So now because you have already learned this, we just go through some review some basic concepts here. So we are first dealing with a single degree of freedom systems. Right, so you have the basic element, mass spring. So this actually is a damper. The dashpot is a damper. Just made to draw like this. So it's called a dashpot. Right, so for the mass model here is first is single degree of freedom. So you have this vibratory system. Right, so you have spring force, F K equal to Kx, damping, Fc equal to C x dot, C is damping constant, okay? But you remember that for this damping force, so it's opposite to the velocity, right? Right, the direction. Right, so for the equation of motion, so this is our step one, mathematical modeling. Step two is governing equation. Right, so for equation of motion, so you start with a free body diagram. Right, so when you analyze, so this actually is very important, but oh, sorry, this is like it's very important thing to do. Okay, but unfortunately, many students they are very reluctant to draw this, but this actually is very essential step to draw the free body diagram to analyze the force. Okay, if you're doing using Newton's law. Okay. Right, so here, so this example is you have a translational motion as well as rotation motion. So here you have a translational motion and a rotational motion together. Okay, we both have translational. Translational, the Newton's law is F equal to mx dot dot, F equal to ma. Okay, x dot dot is double dot, S is acceleration. Okay, right. Right. So m equal to I theta dot dot. If you count I theta double dot, if you consider rotational motion, right? M is the moment. Okay, right. I is inertia, right? Rotationary inertia, right? So here for different type of a, you have different I. So if a cylinder, how much is it? Right, if it's a cylinder, I is equal to half mr squared, right? Right, for different type of uh object, so you have different rotational energy inertia. Okay, so you also have a table. Okay, but if you are taking a test or exam, it will give to you. But very likely we will change to other assessment. Okay, so so you might need to check the table. Okay. Okay. Right, so this is using free body diagram. So this is using the Newton's law. So another method is using energy method. Right, so energy method, you consider the energies. So I have kinetic energy, probably translational or rotational. I see there is a formula here, right? So kinetic energy here, translational half mx dot square, rotational half I dot. Sometimes is using g. Sorry, sometimes using g. So it's the same. Just a symbol difference. Okay? Difference of symbols. So actually express same thing. Right. So if translational or rotational, so it just both these two. For this one, you have both. Okay. Right. Kinetic energy and potential energy. Right. Potential energy of the system. I have three potential energy. V equal to half k delta squared. Right. Potential energy due to gravitational force. V equal to mgh. So here is something that you might need to notice later. We will talk about this one later. Okay. All right, so here the H is the you need to have a reference position. So at the reference position, the potential energy is considered to be zero. Okay. Right. So for example, you have like y like this. So your mgh mg y here will be negative. Okay. Here it will be positive. Okay. Okay, so come back here. So if it's a conservative system, t plus v equal to constant. But if it's not conservative system, right? So dt over so if this one, so dt plus dt over dt, right? So this one dt over d. Sorry, zero, right? So if we non-conservative system, so you just add the change of the work down. Okay. dw dt equals 0. Okay. Right. So here actually is an important point. So I want to draw your attention here is the effect of gravitational force when you have a spring. So you can see, maybe you might already notice. So we will not consider the mgh. Okay. In many cases, if you have a spring connected to the mass, because this mg, right, so this mgh has been compensated by the static deflection of the spring. Okay. So actually, if the mass is connected to spring, so you no need to consider the mgh. So anyone has question here? Do you want to? Do I need to show why? So if you have a spring, you have a mass hand on a spring. So when it's in a static equilibrium position, the spring is already stretched delta st. Okay. Right. Right. So the energy right? The potential energy by mgh actually is compensated by the potential energy of the spring. Okay. Right. So in many cases, you no need to consider if you have the mass connected to the spring. Okay. No need to consider mgh. Okay. This is for linear springs only. Right. If you know, interested to know why, I remember, where remember we have some on our learning guide. So I don't know whether you take a look at the learning guide or not. Okay. So on page 49, they has explanation why you need to consider this. Right, but this actually is important when you formulate the problem. So if you don't know, so you can go take a look. The more detailed explanation is on the learning guide, but not this one. Right, so the learning guide. So here actually explain page 49. So explain why the understand the effect of gravity vector in the equation effect gravitational force on page 49. So actually it will come out right mg equal to kx s. So we will still have the same mx dot plus kx equal to 0 for the equation of motion. Right. So the gravitational force has been compensated for the static of spring. Even you consider the static deflection here, later you will still cancel it out. Okay, cancel it out. Right. Okay. So if you not, you can read this part. Okay. Right. Page 49, 50. Right. So here is when you have the right. So this is a natural frequency, as I mentioned. Why we want to know that now is we for many machines we want to avoid the external excitation should be away from natural frequency. Otherwise, it might have the resonance. Or we can specially design dampers for it. Okay. So natural frequency omega n. Okay. Right. If you have the equation here, then omega n equal to k root k over m. So natural frequency have this relationship f. Okay. The natural period tau. Okay. Right. So for if it's a free vibration, So for this mass spring simple system, the governing equation we derive is mx dot dot plus kx equals 0. So the natural frequency is like here. Right, the free vibration response. So if we so this is come to step 4, right? Interpretation of the results or the solution of the right, solution of the equation. Okay, solution of the equation, interpretation of the results. Okay, so here is you can have this free vibration response in this form. So this two is alternative to each other. So anyway, you have yeah, right. So you have two constants here, A and B. Okay. So for this alternative, you have C and phi 0. Okay. Also, is two constant here in your solution. Okay. Right. Omega n you already get from here. Okay. Right. So if you want to know some relationship between A and B, phi, so you can take a look at it here. Okay. C equal to root A squared plus B squared. Phi equal tangent B over A. Okay. One reciprocal of tangent B over A. Okay. Right. So here, so this actually is equal to each other. Just constant different. So what is expressed? So remember, C is vibration is oscillation repeated motion. So here is a response. So here actually express the time. This is one cycle is 2 pi here. Okay. Right, so phi is a phase. Okay, phi is a phase. So here phi, right, either is lead or lags by. If it's in front of is lead. Okay, if it's starting from here is a lag. Okay, okay. Right, so see here. So we can take a look at this one. So this one. So this is in a sine form. So you know the sine form, right? Right. So it's like you have this. This is sinusoidal form. Okay. Right. So this is a sine form. So C is the amplitude. Okay. Right. C is the amplitude. Omega n is related to the frequency. Right. Right. So from here is 2 pi 1 cycle. Okay. T is a time. Phi is the phase. Okay. Right, so you can see this oscillatory motion. Okay. If you take a look here, it's just like this here oscillate here. So positive x come to this way and then back and back. Yeah, right, like that. Okay. So here you know, so it doesn't matter here x or y. So actually, probably you can see this is x. I'll probably change. Right, x 0. Okay. So depending on which coordinate you are using. Okay. Right, so x is also here because here is right and y. So this is depending on this curve through here. So if you're using the equation, so this should be x. Okay, right. So here, when the t equals 0, then it's a displacement at here, right? right? So y dot is the velocity at t equals 0. Okay, so you can find the initial any displacement of velocity and acceleration, right? So for your interest, okay, right? So this is interpretation of the results. Okay? Right. So this is for free vibration. Right. So this is a solution for free vibration for this governing equation. So later, if this might be more complex, but anyway, you can organize to this form. Right. So probably here you have that equivalent, K equivalent. Okay. Any questions here? Otherwise, we will take a break. So we will take a break, okay, until 3 p.m. How about 3 p.m.? Which F? Oh, it's 2:30. Well, which one you're talking about? Yeah, because when I'm looking at the PPT, I cannot see the message here. So I don't know which F you're talking about. Are you talking about the cantilever beam? Right. So it doesn't matter. You can tell me later, or you can send me a private message. Right. So we'll take a break. So we're back at 3 p.m. Okay. We are back at 3 p.m. I will stop here and uh, if you have any question, free to ask. Because I take a look because I want to use my pen. So I cannot directly use the canvas. I mean, cannot directly use shared files. So I cannot see your message immediately. So yeah, of course. So I'll do that during the break. Okay. Right. So we'll take a break now. Okay. So I will come back at 3 p.m. Okay. Okay. I have sent by email. Will you check whether you get the file? As many of you ask. It's a RMIT email. Don't check the VTC email in your RMIT email. Right. Please note that I don't have access to send you to your VTC email. So any email I will send is to your RMIT email address. I don't know how many of you have come back. Probably I have a small polling here. So I want to check whether you can hear me clearly and follow the slides smoothly. So before I record, you can give me some feedback. Okay, good. So you can use your, so you have already received the slides. Right, so for the right, so for Wenyun, so if you, I have made you a presenter, if you have question, you can right now. If you can use in the share function. Because when you are a presenter, you have the on the right corner. There is probably I can show you now. I don't know how many of you come back. I show some basic functions. Because when I show in the whole screen, it will come a series of screen. Right, so now that you just take a look at the control panel. If you press a purple, right? So here you can chat attendee. Here you can see share. You can use black whiteboard, okay? Or you can share the if you open PowerPoint or Word or Excel, it can share the application. If you can also share the Google Chrome tab, okay? So you can also share the files. Okay. Right. So because whether it's smooth or not really depends on both of us, the connection. Right. So for those maybe you can right, because I'm close my door, I cannot open the door, otherwise the kids might come in. And but when I close the door, the Wi-Fi signal is not is become weaker. But I have found a, repeater here, but it doesn't work. But anyway, it works okay. But in case, sometime I don't know because I'm using. Sometime it will suddenly stop for unknown reason. But if that happens, you can with me for a few minutes. Okay. Right, right. So we will start our right. So I can also leave some time after the lecture. Give probably not because I have another appointment. So if you have question, you can also ask me after the lecture. Okay. We will leave 10 to 15 minutes. Okay. Or maybe to you if you have any question to ask. Okay? Right. If you don't want to, if you don't want to, if you want to show anything now or after the lecture, okay? Probably we start the lecture first, okay? Right. Right. Okay. So we start lecture first. Anyone who want to discuss after the lecture, you can raise your hand or you can type a message after the lecture. Or if we have time, after if we have time, okay? If we can have a Q&A time. Okay? Right. So now in order not to, I will make you a participant. Okay. So we will take a look. Basically, we will take a look at some example questions. Right. So you can read the question first. Before we start to solve them. One. Okay. So we come to the question one. Okay. Question one. Three springs and mass attached to a rigid. So here it has information. Here are rigid weightless bar PQ. Okay, as shown in the figure. So we know you consider its mass. Okay. And also elasticity of the bar. Okay. Find the natural frequency of vibration of the system. Right, how we can solve this? So this has a concept of the equivalent string. So first we can take a look. Is this beam here has a pin support, okay, a pin support, which means a pin support so they can free to rotate, right? So it's not the cantilever beam. Right, so here actually there's not only one way to solve the problem, so we have a different ways to solve. So here suggests one way is find a equivalent spring for K1 and K2. Okay, so here you can see there's two springs connected to the bar, right? So we it's too complex, right? You think it's too complex, and what we can do is so we can cancel this out. So we use a different color, probably red, right? So we can cancel this. So we use one spring to express. So this is a pin support. So actually we will have a K equivalent. K1 to equivalent to replace K1 and K2. And then we will have K3 and the mass. Right, so we need to find equivalent spring to replace K1 and K2 because there are two of them, so make it a bit complex. So we want to find the K equivalent for 1 and 2. And then because here it has another spring K3 and the mass, so we will remodel the system like this. So here the problem here is find how much is K1 to equivalent to replace K1 and K2. Right, so here we can use the energy. So probably here I add one more empty slide here to replace it. Now how to replace? Right, so I can write here, right? You can also see. So it has enough space. So probably not necessary to add a empty slide. So come back here. So here, perhaps you'll use this is name black color. Okay. Right, how to replace this one? So we using the energy to replace. Right, so use the potential energy to find the K1 to equivalent. So they will become, remember the potential energy is half K delta square, right? Okay. Right, so you can think about when this move, remember when this move to this position, how much here will move, how much here will move. Right, so if this is, for example, this moves theta here, okay, so how much is here? So the delta here is theta L, right? Sine theta is very small, okay, because let's say we use approximation sine theta equal to approximately equal to theta. Okay. Right, so here is this delta is theta L for K1 to equivalent. For K2 here, so here is theta L2, right? Right, so here is theta L1. Right, so the K1 to equivalent, so we can get from this potential energy here. So we use, let me see how to, probably right here. right here, so 1 over 2 K 1 2 equivalent, right? Theta. So the total distance here L3, okay, L3, theta L3 square equal to 1 over 2 K1 2 L. So this is L. Okay, L2 square. So here is square. Let me write very well. Square. Okay. So you can here you can find out K 1 to equivalent. Okay. Right. So after you find out the K1 to equivalent, so actually you can find the natural frequency of the system, right? Right. The whole system actually is become right. So it's become like this. K1 to equivalent K3 M. Okay. Okay. So here you already know K1 to equivalent, right? So you and the K3. So this is in the Sarah, right? So you can find the K equivalent. So we use another 3 to replace this. So this 2 is a Sarah. So it become, we use another color of spring, also become right. So this is K equivalent. So actually we will finally we use this simple spring mass system. Okay, simple spring mass system. Okay, so I will stop here first because I forgot to record. Okay, so I will start record now. So I should record. I forgot to record from the beginning. So here anyway. So we have this question. We have 3 springs and mass attached to a rigid the bar PQ as shown in the figure, and find natural frequency of the vibrational system. Right after we analyze the system, we find equivalent K1 to equivalent to make it simple to analyze. So we find a K1 equivalent to replace K1 and K2. Okay. So we from here we come to this one, K1 to equivalent. So we what is K1 to equivalent? We get from the energy using the energy, right? From the energy, right? So we have 1 over 2 K1 to equivalent theta L3 to the square equal to this 1 half K1 theta L1 square plus 1 over 2 K2 theta L2 square, right? Right. So this is delta for each spring. Okay. Right. So after we simplify the system to this one, then we have a K3, K1 to equivalent K3 is in the Sarah spring, right? So we further simplify to this one, K equivalent and the mass. So now our problem come back how to find out a K equivalent. Okay. Right. So this from here, actually, we can get K1 2 equivalent actually equal to K1 1 square plus K2. So this is mathematics. You can back and do by yourself. L3 square. Right. So this is we get from here. Okay. From here. Right. So now we want to find the K equivalent. So this is in the zero screen brain. So K zero is K1 2 equivalent plus K3. Okay. So we can get K equivalent. Okay. Because the extract form is kind of a sorry. So complex. So here, after we get this, so we can get very simple is we can get omega A. Because we have already simplified is to this M K equivalent, right, system? Right. So we will get omega A equal to root K over M. So this is we already derived before, right? We already derived from the this free vibration, this one, okay. Right. So is this K over equivalent over M? Okay. Right. K equivalent over M. Right. So is the root of something. Okay. So some solution I will send you later after the review workshop. But not all. Before I only send some, most of them, but not all. But I will check later. Okay. Do I need to write down, or you can do by yourself? Right. So any questions here? Otherwise, we go to the next example. Right. So here is basically just the introduce how you the model the right how.
Sorry, may I write down the above?
You write could you tell me their name? Your name, so I can make you a presenter. You can write. I see. I know because for me, I didn't show up the. Probably you have the. I don't know whether it's right or not, but you can check. You can tell me your name. I'm making your presenter and try whether you can write.
Yuan Chi Wing.
Xie Ming Yun 係咪？係 Ming Yun。Right, so you can write. So if you someone you can take a look at the question too as well. Because I already sent the file to you. Right, so probably you can also write and on your maybe open any PPT or PDF file or anything. You can share the file or share the screen with not the screen. Or screen has the you can share the application later. Okay. So any questions? Right, any questions? Right, otherwise we go to the next uh question 2. Right, if you're ready, you can tell me. If you already you can write on your PPT or Word, or even you take a photo of your scratching, then you can share the files. Right. Anyone want to share your scratch? You can tell me. So otherwise, I continue first. Any questions? I can I'll continue first. So right. So we can you can write on your piece of paper and take a photo as well. Okay. Okay. Right. We go to question 2. Right. So this is so this problem actually is not it's not complex problem. It's just the help you to see how to model them. Okay, I'll give you things of a modeling from real applications. Right, a loaded mine cart is a mass of 2,000 kilogram. Is being lifted by a frictionless pulley and a wire rope, as shown in this figure. Find the natural frequency of the vibration of the cart in a given position. So this is asking you the natural frequency of the system. Okay, right. So what is this system? Right, so you can think about how to model them. Use the mass spring damper, but because we are now still in free vibration, so there's no damper, undamped free vibration. Right, how to model this? Okay, so I guess here you have some information is missing. Sorry, it comes from. So here is the information. Some information is missing here. Is the so here diameter is given. So I think the missing information here is the Young's modulus of the rope. So Young's modulus of the rope is how much? Oh, it's too small. Against 2 0.07 times 10 to the 9, I think it's gigapascal, Pascal. Okay, so it's 207 gigapascal. Okay, so here is the rope has elasticity, right? So now you know how to model, right? So we back here from this this one, right? So similar, the rope is similar to this rod, right? So the spring constant K is AE over L. K, right, equal to AE over L. Okay, K is called AE over L. So how you can model this? Now you know, right? Right, so actually, so this system is modeled like this, right. So actually, it's models like this, but that is in the inclined plane, right? So you have this. This is K1, K2. So this actually is shorter. So this is long. So it doesn't matter. So it's K1, K2, and M. Okay. So this system actually can be modeled like this. Okay. But this actually is in inclined plane. So because it's in this direction. So it, this direction. So it's the same direction here. So here X. Here X. Okay. Right. Okay. So we can now is this model like this. Okay. So actually, okay. So what you can get is K1. How much is K1? Right. So how much is K1? Right. So K1 is AE over L. So A actually is already tell you. So here you just see that this L is different for these two cable. So here is AE over K1 is 7.5. K2 is AE over 9. Okay. So here you can just use all meters. So this 1.3 millimeter is pi r square. Okay, is pi r square r 1.3 10 to the meters, centimeters. -3. Okay. Pi r squared. E is 207 10 to the 9. So now we all use Newton the meter, so you can get K1 and K2. Okay, K1 and K2. So here the K1, after you calculate, like K1 is 30.53 Newton per meter. K2 is, so this is 9 meters, so this is different. So this is, oh, sorry. So so this is 36.63. So this is bigger, this smaller, 30.53 kilonewton per meter. Okay. So here you can see that so this tube spring is in the parallel position, right? Right. So the K equivalent is K1 plus K2 for parallel springs. Okay. So here you can simplify the system. So how much is the natural frequency? Right, so it's K over M. So here, because I don't want to go through so this omega actually is to say K equivalent over M. Okay. I don't know whether you have because before we have other exercise showing that in the inclined surface, so your omega is still equal to K over M. Right, so your omega N is still equal to this one. There any questions here? Right, so on the inclined surface, so with springs, so actually is the form is still mx dot. So this you can derive. If you consider inclined plane, actually you have the same. Do I need to show you why? So I remember there's exercise. I don't know whether they show you in the class or not. Probably I check here. So that you can derive by yourself as well. So even you consider the inclined plane, so the delta st K1 plus K2 actually equal to W sine theta. Okay. So this actually will help you to remove. Right. So you will still get this M this is a very simple form, mx dot plus key equivalent x equals 0. Okay. Do you want me to show you how you derive this form? Right. Probably let's see the time. So we can consider this as an inclined mass like this. So this will like something like that, right? Right. So this is same to this inclined surface K1, K2. So this is a mass. Right. So this is W. Right. So this is W sine theta, cosine theta here. And so this is 50 degree. So we can use the theta to express this. Well, if you consider using the Newton's second law, so this is the coordinate x, coordinate. Right, so you can simplify like this, right? So if you don't know why liter is become this one, right? If you don't know why it become right y omega equal to root k or m, so you can back and derive from here. Right, so this is the same system here, right? Right, so if you're using the Newton's second law, so you have m, you have F equal to mx, so mx dot because this spring force is here is negative to k1 x plus. If you consider the static deflection, so this is a real force, is k2 x plus. They are the static equilibrium, right? Okay, then plus w sine theta, right? So because you know that, so here you have w sine theta here, and then you have two spring force here. Okay, two spring force here. Right. So when it's in the equilibrium, when in equilibrium, if then right, so you will get WST x1 plus x, also not x, k1 plus. Pi equal to W sine theta. Okay. Right. So here actually you so this is cancel out. This cancel out. Okay. Cancel out. So what you left is mx dot plus k1 plus k2 x equals 0. Okay. Right. If you are not very sure how this come out, right, you can further analyze here. Right. Any questions? Right, no question. We go to the next. Oh, okay. So here I give you an answer here, right? So you can check by yourself the answer. So omega n. After you calculate, so omega n actually is 5.7948 reading per second. Okay. Okay, so here is omega 2 pi omega n tau. So I forgot. So here has a typo. So probably I add now. Otherwise, probably later will just say forgot. If you don't mind, so I just add one more symbol here. Okay, not here. I don't know symbol. So okay. So I just write here. Sometimes there's some typos. But if you don't correct, later you just forgot me. But any questions? Otherwise, we go to the question 3. Okay. Right. So this is involving some calculations here. So I didn't as well. So you can read the question first. Right. Right. So when a 2-kilogram cylinder is suspended from spring, the spring is stretched by a distance of 40 millimeter. What will be the natural frequency in hertz? And so ask for frequency, okay? Not right, not natural frequency and the period. Right, so frequency is in hertz. Ask use actually. Right, so you can think about how to do this. So this is a rather simple question. I'm trying to find out my formula. It doesn't matter. Okay, so here so you can just write down the given. Right, so you have the cylinder spring. So very simple system. So probably just like this. Spring. You have a cylinder. So with you have km. Okay. Stretched by a distance 40 millimeter. So actually it tells you the D static equilibrium is 0.04 meter. Okay. Right, so here, because this is a quite simple system, so we can just use the omega equal to K over M. K over M. So here we just want to know how much is K. So K is equal to P over delta ST. So P equal delta STP here is mg, right? W, again, W over delta ST. So it's 2 times 9.8. How much? There is probably more, but I can only remember 9.8. So here, no matter, doesn't matter. So here is 0.04. Right, so you will get the K. Okay. Right, so very simple. Omega A equal to K over M. Okay, so here is what will be natural frequency and the period for a 0.5 cylinder suspended from the same spring. So this is very important. You read the questions, not true. Okay. So here then is just the K here. You after calculate is 9.81, right? Right. So is 0.5. So here this is a very simple calculation, but probably we will have multi-choice questions. Then they are all simple questions. Right. So here is so you need to 4.5 over m 0.5. So here you have the omega a, right? So they ask in hertz. So F is equal to omega n over 2 pi. Right, so here is 31.32 read per second. Okay, right, so here you will get F. Right, so your period. So period is a tau, right? It's 2 pi F. Oh, no. Right, so the period here, tau, is 2 pi over omega n. Okay, so you can find the frequency in hertz and the period. So here is don't have the answer in period. Right, so only frequency, only the in hertz. So you can calculate by yourself then. So this 4.98 hertz. So period you can calculate by yourself. So this is a relatively simple question. So, but then probably will be something like if we have multi-choice questions, something like this. Right. Any questions? Right, if no question will come to the last example, okay, for today. So last example is actually calculate the response. Right, so question 4, 25 Newton weight is suspended from a spring. So this is also a simple system. A weight is suspended from spring as a stiffness. So actually is like a very simple system like this. Okay, K and M. Okay, right. The weight is given an upward velocity of 5 meters a second when it's 40 millimeter above the equivalence that equilibrium position. So this determine the displacement response of the weight, and so this displacement response actually is asked you to calculate x, okay, xt, okay. And its maximum upward displacement. Okay. Right, so this is the magnitude. Right, assume positive displacement is downward. So here it tells you this is x. Okay. Right, so you can see that this is undamped free vibration. So the general solution for the undamped free vibration is in this form, x equal to because here using A, but it doesn't matter. You can use C. So any symbol is fine, as long as you give him a form like this. Sinusoidal form is the amplitude and the phase. Okay. Right. So in the formula given to you, or in the learning guide is my use C plus 5. So it doesn't matter. So it doesn't matter. Okay. I'll probably just add the 5 arrow here. Right. So this is the general equation of motion for this undamped spring mass system. Okay. So the initial condition is right. So when t is equal to 0 or up, so here is initial condition is upward velocity of 5 meter second, and when it's 40 millimeter above its equilibrium condition, right? So when at, so this is at initial at t equal to 0. So actually this mass is let me see, probably this one. So at t equal to 0, so this actually is here, somewhere here, above. So this is 40 millimeters. So this is static equilibrium position. Right, so this is 40, and this now they have upward velocity v 5 meter per second. Okay. Right. So at t equals 0, so the x, because you see the positive displacement is downward, so here is negative, x equals negative 0.04 meter, right? Right, so the velocity x dot is, because now you make it downward is positive, so here the velocity here is also negative, is 5 meter per second. Okay. Right, so you have this expression here. So then you substitute inside, when x t equals 0, how much is x? Right, so when t equals 0, right, so when t equals 0, so this is x a sine phi 0 is negative 0.04, right? When t equals 0, so x dot, so here it takes the first derivative with respect to time. So x dot will be sine become cosine a. So you can write it in front of this. So you have this omega n, right? Omega n cosine omega nt plus phi 0. Right, so this is x dot right? So when t equal to 0, so you get this a omega n cosine phi 0 equal to -5. Okay, right? So here is so here you know that there's omega n. Also, omega n is very easy to get. Your omega n is k over m. Also, you have spring stiffness, and this is not m, right? So this is not m. Remember, this is a width. So this is w. Right, so you need to divide by g. Right, so you need to pay attention to this small things. So here, so you get k 0.42 because here is millimeter. Actually is divided by -10, 10 to the -3. So this actually is 10 to the 3. Okay, you change to Newton meter. Right, over m. M is 25 divided by 9.1, 9.81. Right, so you get omega n. Probably I'm writing too messy. We know omega n is 12.83 read per second. Okay, so here you have, so you have derived this. Okay. Right, so after you derive, so here, what we have? We have this one. Oh my God, this is not the highlighter. Hey. Can still see, the yellow one can still see. Here you have this one, right? So you have two equations. You have omega A is known. So you have I'll give a beautiful color here. A phi 0, phi 0, right? So from here you can get A. Okay. So you can sum up A and phi. Right. So you can use tangent. So from here, this one over this one, so you can get a tangent of phi, right? You can get a tangent of phi, you can get a phi. After you get phi, you can get A. Okay. So I'll probably give a empty page. Okay. So here the two conditions you can get is you can have a sine phi, right, over a omega n cosine phi equal to -0.04 over -5, so which will become 0.008. Okay? So you have tangent phi equal to 0.008 times omega is 12.83. Right, so you can get phi is 0.1023 reading. Okay, so this is a phi, right? So after you get phi, phi 0, right? After you get phi, then you can get A, right? You can using A sine phi equal to -4, so you can A sine. So when you use the calculator, remember you turn the radian back to the angles. Okay, so otherwise you will get the wrong answer. Okay, so here you will equal to negative 0.04. So A equal to negative 0. Right, so here you can get the displacement response is right. So here is omega n is here. So okay, so the maximum upward displacement then is 0.92 meter, right? So upward is this one. Okay. Right, so any questions? Regarding this? Okay. Okay, so before we go in, I have another one I want to share you is similar to question 1. I don't know whether you, I see that is already shown here. It's a question 1, similar to question 1, but it's different. Okay. So actually I see. Right, so at some point here, so here for the question 1, so if it's not pin connected, so if it's a cantilever beam, so I didn't draw very well. So this, if it's a cantilever beam, what's the difference? Right, so everything is the same. So actually is a question. In your learning guide, or some of you might notice from the slides given by Sonny. So there is a similar, looks very similar question, but it's not same actually. Let me check. Right, if you have any question that you want to ask, you can prepare now. Also, I can make you as a presenter. You can ask. So I'm now trying to find out the another one. So this is on 63. So I'm going to share another file, the learning guide. So a few minutes. Right. So if you come I don't know whether you read the learning guide. So if you come to the learning guide, I go to page 63. Oh, so probably. Okay, so okay, so I have modified this now. So this don't have that example. Oh. Okay, I show you another. Yeah, so this is some little old file. I open that first. So wait a few minutes. If you have a question, are free to ask me now. So I'm looking for. Yes. Okay. So I find in the PDF though. So cannot write directly. Okay, probably I just draw here. So thanks for your waiting. Here I will come back to this. Right, so we have same, very similar to question 1. Also here is we have also K1, so K2. So here actually you have another way to solve them using the Newton's second law. So you can think about how to use Newton's second law. Okay, so here is a mass. So similar to that one, but here is difference is here. You is not the pin supported. So this is a fixed support. Okay. Right. So if I ask you to solve this one, how you can further modeling this? Right, we use the same thinking, right? So we can find a equivalent for K1 and K2, right? Also here we can become like this, okay? So this is a, because this is a fixed part, okay? Also here, as we mentioned about fixed part cantilever beam, it also has a spring constant here, okay? Spring constant. Right, so here is what you can do is, if you use same thinking, so we can find a K1 to equivalent for K1 to K1 to equivalent, okay, for K1 and K2. So we will just change like no matter what's the position, we will have probably draw upper. It doesn't matter. So here have a K1, K1 2, K1 2 equivalent. Okay. Okay. So this is a little bit different. So here, so you have a K1 to equivalent to find, right, to replace K1 and K2. Okay. Then the beam itself is spring. So actually the system is like K beam and and so this is a mass. So and the K1 2 equivalent. Okay, so this is if you want to further model this, so you can use this equivalent string. So this is a easier way to solve the problem. Okay, so K beam is, you know that, so for cantilever beam is 3 K beam is equal to 3 EI over L3. Okay. So here this, because this is a cantilever beam, so this deflection here is different. So here actually it follows the cantilever beam's deflection. If you go back to the, you can, if you have a computer, you can search a deflection a beam table. So you can find actually there's an expression for cantilever beam deflection is F. F is mg for this case. If you have a mass here, so F here. So I remember someone asked what is F. Probably I answered here. I don't know whether I answered or not. So M is 6 EI 3L minus X. So this you can find from deflection beam table. Right, so we learned in solid mechanics. Okay. So here, because this is not pin supported, it's not theta L, so each deflection here is different. So here Y, you can see Y. If you see Y position A, Y B, and Y L, Y L is different. So Y A is when X equal to A. Okay. Y B X equal to B. Y C Y L. YL and X equal to the whole length is L. Okay, so here you just remember that when you find out the K equivalent, right? So the deflection here is different. It's not the pin supported, it's theta L. Just a very simple theta L1. So here is just say theta L1, theta L2. Theta L1, theta L2, and theta L3. Theta L1. Right, so this is different. You need to use this deflection beam, deflection of cantilever beam for fixed support to find out the deflection here. Right, so here the same. So the other is the same. So you can have this K beam K1 2 equivalent. Right, so you have similar using the energy 1 over tau K1 2 equivalent. Y L square equal to half K1 Y A square plus 1 K2 YB square. Okay. Right. So after you find out this K equivalent, so you keep in. So this is in the zero. Right, in the zero position. Because you move the K1 equivalent to the end of the beam. So this will be a zero in the zero position. Okay. But any questions here? Okay. Right. Okay. So actually, I have stopped the recording. So now still several minutes left. I want to ask your opinion of our lab assessment. So actually we have the lab. You know the lab has using the video. I don't know whether you see the lab materials. So anyway, it's provided by MIT campus. So they record a video. Also, they have a tutor to explain. They have two videos. Right, one is show the experiment. One is explain how to processing the data. Right, so later when you go to the residential visit, so you will also do by yourself. Okay, so what means you can you can keep the lab report because later you probably can use for your residential visit as well. Because you still need to do again because you didn't do by yourself. So any question regarding the lab? You can, if you want to talk, you can just unmute your microphone, or you can send message. Right. So now basically our lab is we have all the materials. Right. So assignment 1, assignment 2 is also so probably just shares the screen. Right, so here actually what I want to do is I want to hear some of your opinions regarding our left assessment. Right, if you have any questions or any considerations, you can free to discuss now because soon I need to set all the assessment, right? So because it's already starting of April and we should finish our assessment, all the assessment during the exam week. So which means we will have the last assessment should be at least due in the exam week. Right, so we come to our assignment. Right, so here assignment 1, lab report. So actually, if you click inside, you will see all the videos and the tutorials and the lab report template and the data. Okay. Right, any questions for the lab? Right, so so basically we will should we have some tests and exam, but there's agreement by ETC and MIT is we need to change the form of the exam because this change to its non-invigilated form, okay, which means no invigilation needed, no one watching you, okay. Right. So any consideration that you want to share here for the left assessment, the test, and the exam. So the exam probably I will separate into maybe 2 assessment. I'll probably give you 2 quiz, online quiz. Or maybe you cannot see a quiz. So any considerations here because later we will set the assessment. You like multiple choice questions or essay questions? Right? No one have any opinion on your assessment? Right, so there's one is we can set the time. You can when you log in, if there's online quiz, you need to log in and complete in a certain time. Is that okay? Yeah, I will have some MC question, but that means it will be all MC questions. Okay. Right. One is because we have we need to change the form, right? But anyway, I should expect similar to the quiz, but maybe not. We need to consider now design. Is after the course review workshop, the week of the end of April, you might expect something like quiz, and in May there will be another one or another two. I probably will separate the two assessment. Okay. Right, MC questions is suitable for online. Okay. Yeah, actually we are asked to try no invigilated exam. So actually we are informed. Okay. But they still need some time to find out how